Welcome to the second part of the video. So this is for experts. Let's get started. Okay, so what I'm explaining here is an application of techniques of non-equilibrium statistical mechanics to this problem of efficiency and power of heat engines. And probably you know that in many applications of non-equilibrium statistical mechanics, we usually treat exotic systems like mesoscopic system, very small system, and so on, where fluctuation plays a very important role. But in this application, we are treating just usual macroscopic thermodynamic system and applying these techniques. So this is one of the unique features of this work. And here we treat general macro process and yes, prove a general trade-off relation, which shows that non-zero heat current implies dissipation. I will explain. And then I will apply this relation to the problem of power and efficiency of a heat engine. Okay, let's go. So I will explain the formulation that we use here. So this just explains you basic setting. So here we take statistical mechanical point of view. So the engine is modeled as a system of n classical particles. Of course, n can be anything that can be very, very large. And the dynamics of engine has two parts. The first part is deterministic dynamics. This is just a Newtonian equation with arbitrary force and interaction. And I will explain about lambda later, but when this parameter lambda is fixed, this dynamics conserves energy and phase space volume. And that is the only assumption. So this describes the internal dynamics of the engine. And of course, the engine is interacting with heat bath. So here we use stochastic dynamics. And to describe interaction between the engine and heat bath, we use Langevin type noise, which describes the effect of T2 or more heat bath. Okay, and important thing is this parameter lambda. And lambda is a parameter or set of parameter which controls the external force like this, or the interaction and the couplings to the heat bath. And okay, so remember we want to treat something like heat engine. So probably it consists of gas in a cylinder with piston, and probably we want to push this piston and pull this and so on, and or sometimes we want to connect the engine to this path, or sometimes connect to this path and so on. So there must be some control, and which should be done in a periodic manner. So we assume, actually I already said this in part 1, but we assume that there is an external agent which controls lambda according to a fixed protocol. So that's how we realize heat engine, okay? So this is the basic setting, and let me be more precise. Okay, so this uppercase X denotes the total coordinate of the system. System means engine, and it consists of all the coordinate and velocity, okay? And let me start from deterministic dynamics with fixed parameters. And then this is simply the Newtonian equation with arbitrary force and interaction, which conserves total energy. So this is just the Newton equation. And I assume that there is a function energy, and it depends on the parameter, and of course it's a function of this coordinate x, and it is conserved, okay? So if you, of course, this x of t is the solution of this Newton equation, and energy is conserved. Very standard. And stochastic dynamics, again, the same notation. And here, P of t of x is the probability density to find the system, the engine, in the state x at time t. And okay, when I first assume that still the parameter lambda, like the position of piston and so on, is fixed, and there is only a single bath. And then in this case, the standard time evolution for this probability density is given like this. So this is time derivative, and it's a sum of two parts. And this first one is simply the Liouvillean corresponding to the Newton equation. So this part just describes time evolution according to the Newton equation with fixed lambda. And this one here describes the standard random noise from the heat bath. So this gamma controls the strength of the noise. Okay? And it is well known that if you solve this thing, and if you consider the solution of this equation, the Kramers equation, and if you take the large T limit, and then this P of T approaches the canonical distribution with respect to this conserved energy, okay? So this is just equilibrium. So, you know, this is a very natural dynamics. And if there is only a single bath and lambda is fixed, then everything settles to thermal equilibrium. Okay. This is the case with fixed lambda and a single bath, but we want to consider something more general, okay? So we want, first of all, we want the external agent to control this lambda t according to a fixed protocol, and we assume that this is done in a periodic manner. So this lambda t is a function of t with period tau, and this tau is fixed, okay? Then the Kramers equation or continuous master equation that describes our heat engine is written like this. And this part is again the same thing like here, and it corresponds to Newton equation, but now lambda is time dependent, okay? And here we again have this term which describes noise from heat bath, but we do have, we now have sum over two heat baths, high temperature and low temperature heat bath, and they have different coupling and different temperature, different inverse temperature. Okay, but anyway, this is a very natural one. I mean, if you only have a single bath, then everything goes to thermal equilibrium. We have exactly the same bath, but with two different temperatures. Okay, so this is still very, very standard description. Okay, and still this is also very standard. So I want to talk about the distinction between heat and work. Of course, this distinction is essential for thermodynamic discussion. So first of all, this is the energy expectation value. So this is the energy function, this is a probability density, so this is of course the expectation value of energy as a function of time. And you differentiate this with respect to t, and then of course, if you look at here, you get two terms. You differentiate it here, you get this. If you differentiate here, you get this. And we usually interpret this as flow of work and this one as flow of heat. Why? Well, this one is the change of energy caused directly by the change of this lambda t. And remember, lambda t is a set of parameters that describes the system, but in particular, this corresponds to something like the position of piston. So the external agent is moving this piston. And then the energy changes, but you know, this kind of energy change is usually regarded as work because you know this external coordinate is varied. And this is simply the remaining. And usually when we have energy, the change in energy, which is not mechanical, we interpret that change as flow of heat. And moreover, you can easily find that this part, flow of heat, can be written in this form with JBT defined in this way. This is just an easy calculation, and that follows from this master equation. Everything follows from this master equation. So we can we interpreted this as flow of heat. So of course, it's very natural to interpret this as heat currents from the system to the bath. We have two heat baths, so we can define separate currents from engine to the two heat baths, okay? So these are just very standard setup. So let me discuss our main result, okay? The central quantity is the entropy production rate. Again, this is very standard, nothing original. So this is a probability density to find the system in the state x at time t, and these are heat current to bath, and B stands for H and L, high temperature and low temperature at time t. Then we define, as usual, the total entropy production rate like this. What is this? Well, first of all, this part, H, is the Shannon entropy for this probability density. So this one just, this one is simply the change of the Shannon entropy. So, I mean, Shannon entropy is defined in this way, so it's a very microscopic quantity. I mean, P of X describes the engine from a very microscopic point of view, and so this characterizes a system from very microscopic side. And this is the such microscopic entropy, and this is the change of this entropy. And here we have entropy production rates in the bath. And in this case, we take macroscopic point of view. So this beta j is nothing but this the time derivative of this well-known formula in thermodynamics. So this is the change in entropy. So yes. So interesting. So this is very standard expression, but interestingly, this is sum of two totally different types of entropy production. This is microscopic entropy production, and this one is macroscopic entropy production. And everything, sigma t, contains both of them. Okay. Now, we can state our main inequality by using this entropy production rate. Okay, this is I already defined. And this main inequality is something I call the improved Shiraishi-Saito bound, and it looks like this. Okay. First of all, we know that this quantity sigma t is non-negative. Okay. Always larger than or equal to 0. But we have much improved lower bound for sigma t, which looks like this. So the left-hand side is simply the sum of the absolute value of the currents, heat currents, and on the right-hand side we have square root of sigma t. And this theta t is a new quantity which is defined in this way. It's a bit complicated. This is the strength of noise and so on. But I say that this quantity basically reduces to the heat conductivity when the system is close. The engine is close to thermal equilibrium. So it's a complicated quantity, but you can think of it as something like heat conductivity. Okay. So this is what we prove, and what does it mean? Well, I would say that this implies that whenever you have non-zero current, you must have non-zero dissipation. So if sigma t is 0, then no entropy is produced. So we don't have any loss. We don't have any dissipation. But if we have non-zero sigma t, it means that we have some loss and some dissipation. So this tells you that whenever you have non-zero current, you must have non-zero dissipation. And this actually implies our main conclusion that we discussed in part 1 about the efficiency of, about the power and efficiency of heat engine. So suppose that a heat engine has non-zero power, okay? Unlike in Carnot cycle, assume that a heat engine has a non-zero power. That means you have to have non-zero exchange of heat current between the engine and the bath. So that means you have non-zero current, okay? But then this improved Shiraishi-Saito bound tells you that there is non-zero dissipation unless this theta is infinite, but this theta is finite. So this means that you must have non-zero dissipation. Non-zero dissipation means that you have some loss, and that means you cannot attain the maximum efficiency. So this is a rough story, but let me make this statement here more precise. So actually I will discuss the proof of this very interesting inequality later. So let me show you how we apply this problem, this inequality to the problem of this efficiency and power. Okay, so let's go. Okay, so this is the basic bound. And first of all, I integrate this over the period of the heat engine. Tau is a period, so that I integrate this from 0 to tau. This is simply, and then I use Schwartz inequality here to get this. Okay. Now here, okay, so remember this is the definition of sigma t, the entropy production rate, and here I have the integration of an entropy production rate. So let's consider this integration, and then since this is a definition, I get two terms. One is this for Shannon entropy, and the other is this for macroscopic current. Okay, then I say that we can assume that this P0 is periodic in time. And this may not be true in the beginning, but suppose that you operate this heat engine for quite a long time, and then you can show that everything settles in a totally periodic manner. So you can safely assume that P0 equals P tau. That means if you integrate this from 0 to tau, only when you integrate this from 0 to tau or some integer multiple of tau, this Shannon entropy part vanishes. This is very important because Shannon entropy is some totally microscopic and complicated object. And so it's very hard to treat a theory which contains this explicitly. But here, this simply vanishes. Okay, so here I got two very important bounds. So one is this one, and the other is this one. Okay, so I want to keep these two important inequality relations here, and I simply combine them. So I square this, and define theta bar as the time average of theta t, and then you get this here. And here, I made use of this equality here. So I get this inequality, which is very interesting because we are using microscopic theory, but this inequality involves only this heat current and this quantity theta bar. So you can say that this is a kind of thermodynamic type inequality which only contains macroscopic heat currents. Good. Now the goal is very close. So we have this inequality here. Let's apply this to this setting for heat engine. And then this is QH, this is QL. Be careful of the sign because of the sign convention. And then we simply plug this in here. And you can easily find that this inequality reduces to this one. Okay. Then it's not hard at all to rewrite this in this form. Oops. Let me say, we write this in this form, and we get this rigorous and quantitative trade-off relation between power and efficiency. Okay, so this is something I already discussed in part 1. So this implies that a heat engine with non-zero power can never obtain the Carnot efficiency. So let me stress that this result applies to any heat engine that can be described by classical mechanics with or without time reversal symmetry and Markov process. And I also stress that we don't make any assumption about the state of the heat engine. So the state of the engine can be arbitrarily far from equilibrium. So this is a very non-equilibrium result. Let me also make a comment about this quantity theta bar. So it's defined in this way, and theta is defined in this way, and this important function gamma b applies here, and this so describes the strength of the noise. And of course, I first can emphasize that this theta bar is not a universal constant, of course not. But from this, we can show that it is always finite. And also, I say that this theta bar is proportional to the size of the system. So it means, or if the heat mass and the engine is just connected by boundary area, then theta bar is proportional to the size of the boundary. So anyway, I want to stress that this theta bar is a very physically natural quantity. So, so our bound is meaningful also in thermodynamic limits. And also, as I said, this theta bar approaches the heat conductivity kappa in the limit of equilibrium dynamics. Okay, so it's a kind of renormalized heat conductivity. Okay, so that is how we derive this important relation starting from this improved Shiraishi-Saito bound. So let me use some pages to describe you how we derive this important relation that I call improved Shiraishi-Saito bound, but not in the present problem. I want to discuss a very simpler problem, but from which we can learn the essence of the proof. So I treat a general Markov jump process, and I want to prove this thing. This is the improved Shiraishi-Saito bound in this case. Okay. And I hope that many of you are familiar with Markov jump process, but let me just explain. So it's a stochastic process in which state space is finite and discrete. So this is a state space, and it consists of finite number of states points, like x, y. And lambda is again parameter, it's again a parameter or parameters of the model. And E lambda of x is the energy of the state x when the parameter is lambda. And I want to describe stochastic process, Markov jump process. This is a master equation. So in order to do that, we need transition rate, R lambda of x, y. And this satisfies the usual condition that this is negative when x and y, the two states are different. And if you sum over the first one, you get 0. Okay. And in addition, I assume that this R satisfies the detail balance condition with respect to the canonical distribution at a single temperature beta. Okay. And this is the relation. Okay. The very standard relation. I assume that this is true for any x and y. Okay. And then the story is the same. The parameter changes according to a fixed protocol lambda t, and px of t is the probability to find the system in the state x at time t, and this is a master equation. Okay. Now lambda changes according to the fixed protocol. So this is very standard stochastic process. And here I want to prove this inequality. So first of all, I want to define entropy production rate and heat current. And again, this is very standard. So this is entropy production rate. Again, the change derivative of the Shannon entropy and beta j. And heat current J is defined in this way. And again, I say this is a very standard, and you can easily find out what does it mean. Okay. So this is standard. And if you plug this in, and if you use, this detail balance condition, you will find that you can rewrite this entropy production rate in this very beautiful form. This has a form of relative entropy. And this is, again, very standard and very well known. So this sigma t, this is a standard definition, and this is a standard, very interesting expression. Now, I sum this part and the same thing with x and y flipped and divide by 2 to get this thing. This is an easy thing. And then you look very carefully to notice that these two guys are the same, and also these two guys are the same. And now there is an inequality that you can easily show, which looks like this. If you have this form, it's lower bounded by this. Then, of course, you can apply this inequality to this here, and you find that these guys are like this. So we get an inequality, a lower bound for sigma t, the entropy production rate. This is lower bounded by this quantity, and this is very important, so let's keep it here. And now I want to discuss an upper bound for the absolute value of the current Jt. So this is current Jt, and here I added something which is just 0. So if you sum over this y, it gives you 0. So this is just 0, but I add this. And then I add the same thing with x and y flipped and divide by 2 to get this. And now I do something tricky. I multiply everything by this and divide everything by this. Why did I do this? Because if you square this, you precisely get this thing, which appears in the lower bound of the entropy production rate. Now I take the absolute value of J and I Schwartz. And then I get the square of this thing, which is written this way. This is a very natural quantity. You're summing over all the jumps from state y, and you're also averaging over y. And here you're averaging the square of the change in the energy. Very natural quantity. And this is the definition of theta t in this case. And of course, if you square this and sum, you get, oops, sorry. If you square this part and sum over all except y, you get this thing, and this is bounded from above by sigma t. Okay, so you get this. So this is the definition of theta. This is just sigma t, the entropy production rate. So I got this one. So this is the improved Shiraishi-Saito bound in this case. And well, I think this was a simple problem of Markov jump process. And I say, but I ensure that this just tells you the essence of the proof of the real case. So this is just a minor comment about how do you treat the full model. So the master equation, Kramers equation, looks like this. And it's not Markov jump process, or it doesn't satisfy detail balance in the most naive case. But you can, for example, here, this never satisfies detail balance, but this term does not produce any entropy, so it's safe. And here, also, it does not naively satisfy detail balance condition, but this can be written as a continuum limit of a discrete model with detail balance condition. And this actually comes from the symmetry, a reflection symmetry in the transition rule. Well, you can find details in our paper. Okay, so here's the summary. So we have proved a trade-off relation that I called improved Shiraishi-Saito bound. Oh, because these are two collaborators of mine, and they had some work before this collaboration, and they had an early version of this inequality. And this trade-off relation shows that a non-vanishing heat current always implies dissipation. Very interesting. And this bound is essential, but when applied to the problem heat engine, leads to a trade-off relation between power and efficiency that I discussed in part 1 of this video. And this implies that a heat engine with non-zero power can never attain the kernel efficiency. Okay, so that's basically what I wanted to say. So if you're interested in more details, please take a look at our So if you're interested in more details, please take a look at our papers. And if you go to the web page, which is linked from this video, you will find links to our papers. And there, in these papers, you will find more details and references and so on. So thank you very much for watching. Goodbye.